Okay, today we are looking at the best choice to solve systems of equations. And so we want to use our time and energy efficiently when we are solving systems of equations. So it's worth taking a moment at the beginning of a problem to decide which method would be the most efficient method. So let's just do some sample problems together. In this first grid here, we're not going to actually solve these. We'll just look at what is the best way to solve and why. So when we look at this first example, we see our x's are lined up, y's are lined up, equal signs are lined up, and our integers are lined up. So these are both already in standard form. So the best method here, the most efficient method here, any method will work, okay? And there's really no wrong way. You can definitely solve this by graphing, substitution, or elimination, but because these are already so nicely set up in standard form, the most efficient method would be elimination. Okay, so both equate, and we can see obviously even more clearly our y's are already set up to eliminate. When we add them together, they'll cancel out. So both equations are already set up in standard form. And that'll make it easier to solve using elimination. All right, when we look at example 2, we can use graphing. We could also use simple substitution. Since they're both equal to y, they're both equal to each other. But when we're looking at the 3 key choices here, substitution, graphing, or elimination, when we have a 3, choose each one once. So in this case, realistically, I would do simple substitution and set these the right-hand side of each equation equal to each other. 2/3 x minus 5 equals 3x plus 2. Solve for x, substitute it in for y. But if we're having to choose which of the 3 is best, it looks like this will be substitution because the x is isolated. This will be graphing. You definitely could also solve this with simple substitution. Okay, so both equations are already in slope-intercept form with graphable y-intercepts. So we can easily graph, these are whole numbers, -5 for a y-intercept here, +2 for a y-intercept here. So both equations are already in slope-intercept form. And conducive to graphing. Okay, so conducive to graphing, not only because they're already in slope-intercept form, but we don't have a number like -5.275 here that we're being asked to graph. It's an integer. That's an integer. Rise over run, very straightforward. I can go up to over 3. So these are very conducive numbers to graphing. They're friendly numbers for graphing. And then when we look at the third example here, substitution, we see one of the equations already has a variable isolated, or maybe it wouldn't be quite isolated, but it could be, another example might be some, pretty close to being isolated, but the x is already isolated, so we can substitute that in here for this x in the other equation and then solve for y. Okay, so the second equation already has the x variable isolated. Okay, this makes it easy to substitute into the first equation. All right, so that's just when we are given a graph like this, you'll have one of these on your test and you have to choose each method once and substitution, elimination, and graphing, and describe why each of those would be most efficient, why you chose to place them where you did. So let's do a couple of examples together. 3x minus 5y equals -7, x plus 2y equals -6. These are both already in standard form, so that is pretty conducive to using elimination. So let's go ahead and solve using elimination. This is a positive 3x, that's a negative 3x, or I want to make this into a negative 3x. So I can cancel out the x values. I definitely still could cancel out the y's. That would just give me one more step, because I would have to make this into a negative 10y and this into a positive 10y, which would mean I need to do manipulation with both equations. If I cancel out the x's, I just have to multiply the bottom equation. So again, this is a positive 3x. We'll leave that alone. We want to make this a negative 3x, so that bottom equation needs to be multiplied by -3. So the top equation, I'll just bring this right over. 3x minus 5y equals -7. This bottom equation, I'll distribute the -3. -3x minus 6y equals positive 18. I'm just double checking, good. And then I can add these two equations together. 3x minus 3x is 0. -5y minus 6y is -11y. And then 18 minus 7 is 11. And then I divide each side by -11 to get y equals -1. Okay, so the y value is -1. And then we'll substitute that into either equation to solve for x. I'll substitute it into the bottom equation because the numbers are slightly smaller. So x plus 2y equals -6. That was that second equation. And then I'll plug this -1 in here. So x plus 2 times -1 equals -6. X minus 2 equals -6. Add 2 to each side, x equals -4. Okay, so our solution is -4, -1. And we should sub these in to check. Okay, always check those using your check step. Just for sake of making our notes not too long, and I know this answer is correct, I'm going to skip that check step. But again, you should always check it in both equations. Okay, these are both in slope-intercept form. That's very conducive to graphing. So I have some graph paper on the second page for you. So our first line is y equals 1/3 x plus 2. And our second equation is y equals -2x plus 7. Okay, so then I will go ahead and graph those two equations. Our y-intercept here is +2, so I'll start at +2. Our slope is positive, or excuse me, was that positive? It was actually negative. So make sure we have that as negative. 1/3 x. So down 1, right 3. Down 1, right 3 more. Okay. And then our bottom equation is y equals -2x plus 7. So here our y-intercept is at +7. And our slope is -2. So we'll go down to right 1. And I see that's our point of intersection, down to right 1 and continue on. Okay. And then we graph that line. We see our point of intersection is at 3, 1. Okay, so 3, 1 is our solution for that one. I can go ahead and write that here as well. 3, 1. Okay, and then if you were doing this on your test or quiz, you would see the graph on page 2. Okay, make sure you have your lines listed on the graph. All right, next, let's take a look at just a couple more problems. All right, so this problem, we have y equals, we have x equals. They're not both in standard form, so that's not going to be great for using elimination. We have an x isolated here, we have a y isolated here, so substitution, it doesn't matter which one you substitute into which, okay? So let's just go ahead, because it doesn't matter at all. So let's take that first equation, y equals 2, but instead of saying x, we're going to sub in 3y minus 6. Okay, so y equals 6y minus 12, subtract, sorry, distribute here, just double checking my distribution, and then plus 7 is what I forgot. Bring down that plus 7 here. All right, so then y equals, we'll combine our like terms here, 6y minus 5, and then subtract 6y from each side. We get negative 5y equals negative 5. Divide each side by negative 5 to get y equals 1. Okay, and then once we have y equals 1, we can substitute that back into either one of the original equations. Since next I'm interested in finding out what x equals, I'll plug that in here. So the x is already solved for. So x is equal to 3y minus 6. I'm just subbing in that 1. So x equals 3 times 1 minus 6. X equals 3 minus 6. X equals negative 3. So our solution is negative 3, 1. All right, and then for my second, or the next problem, we have 2x minus 5y equals 9 and 3x plus 2y equals 4. Elimination, these are all would be the best strategy. These are both already in standard form. So the least common multiple of 2 and 3 is 6. The least common multiple of 5 and 2 is 10. So I'd rather work with 6s than 10s. So I want to choose to cancel out the x's. Can I cancel out the y's? Absolutely. Okay, either way will work. So here I want to have our x's cancel out. It doesn't matter which one I make positive and which one I make negative. So I'm going to go ahead and just keep my top one positive. So I'll multiply this by positive 3, and I'll make my bottom equation have the negative x. So I'll multiply that by negative 2. So 3 times 2x is 6x. 3 times negative 5y is negative 15y. And 3 times 9 is 27. Negative 2 times 3x is negative 6x. Negative 2 times 2y is minus 4y. Negative 2 times positive 4 is 8. Oops, negative 8, excuse me. And then 6x minus 6x is 0. And then negative 15y minus 4y is negative 19y. 27 minus 8 is 19. So we divide each side by, this is 0, so that's nothing. So we divide each side by negative 19 to get y equals negative 1. And then we can substitute that into either one of the original equations. It doesn't matter, so I'll just sub it into the top equation. 2x minus 5 times negative 1 equals 9. 2x plus 5 equals 9. Subtract 5 from each side to get 2x equals 4. And then divide each side by 2 to get x equals 2. So our solution is 2, negative 1. So those are just some examples of choosing the best method to solve systems of equations.